This is the third lecture for MSU Billings. In this lecture, we will cover the following. First of all, there is going to be a review of the size of the solar system lecture, where you've learned about measuring with angles and how Aristarchus of Samos figured out the size of the solar system way before Copernicus. Then, we will discuss the history of science from the ancient world and until the modern era. Along the way, you will meet a person by the name of Avicenna or Ibn Sena that came up with the idea of inertia. That is the same inertia used in Newton's first law of motion. But before we get into the actual two topics of size of the solar system and inertia, let's talk a little bit about the scientific method, so to speak. Our aim is to show you those hypotheses that would be supported. The scientific method is built in the following way, which will be very familiar to those of you that have started on PHSX 104, the lab part. In that lab part we have an IMRAD method, which basically says the following. Hey, let's observe some stuff. Let's form a hypothesis. Then we will play a little game, for example, clap our hands right next to the rims, maybe a mile from the rims. Then there's going to be sound bouncing backwards, and we will figure out what the speed of sound by measuring the distance to the rim divided by the time it took to go there and back. That's an example of proper science, and when you deal with that, you can support or reject the hypothesis, in that case that the speed of sound is about 1,000 feet per second. Now, in general, that's the whole game of science. That's all we do. We come up with those hypotheses, and we improve on those hypotheses with more and more careful measurements. The hypotheses we discussed in lecture 2 were that the Earth's 6,400 kilometers in radius, the distance to the moon is 380,000 kilometers, and the distance to the sun is 150 million kilometers. What we will start to discuss today is that objects at rest tend to continue at rest, which you could see, for example, in the two videos that I have posted on your D2L site. The video with the tomato and the samurai, and the video with the tablecloth and the dishes. Look it up. Objects at rest tend to stay at rest. Objects in motion tend to continue in motion. We will move to that a little bit more seriously on Wednesday. Okay, time to ask you a few questions. The reason for me recording is so that I time you a little bit. This way you have a few seconds to consider things before rushing to the answer, which is in the next slide. So what I'm going to do is I'm going to whistle a little bit, and when it's done, it's going to go automatically to the next slide in the YouTube video, or in here you just wait until I shut my mouth and then you go to the next slide. Alright? Got it? Da la 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 bum ba-dum bum 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 go. Of course you recognize this from the Jeopardy theme. I don't know how to sing. I apologize if it sounds awful. Not much to say in this particular case. That's what Eratosthenes found. Be a tad more careful with this question. If you didn't get it I strongly recommend that you draw the following figure. In general, when you observe a lecture, it's a great idea to have a piece of paper in front of you, maybe a legal pad, and jot a few figures. It's going to help a lot. On that, you should draw, in this case, a small circle. That's going to be the moon. A slightly larger circle next to it, maybe at a few times the size of the large circle. That's the Earth, around which the moon is orbiting. And light comes from very far away, therefore the lines intersect the moon and continue parallel, so they exactly cast the same exact shadow as the moon. That's in addition to the demonstration at the very bottom here. Okay, actually, as we learned last time, 1 degree is spanned by your pinky at arm's length. Both the moon and the sun are about half a pinky at arm's length. Please don't try that at home. Don't try and cover the sun with your pinky, because if you miss by a little bit, you'll burn your retina. Now I'm going to try and just blabber on for a little bit, and you try and answer the question. Blabber, 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 blabber. Obviously, if the moon is much closer, it is much smaller. The sun is 400 times further out, and that ends up that it means that it's 400 times larger. So let's sum it up again. You recognize the question, like the fact that masts of ship is gonna disappear last when the ship is going away from the harbor. There is a rounded shadow of the Earth on the moon during a lunar eclipse. Then you made a hypothesis that was very reasonable, that Earth is round and it's actually a sphere. The consequences come with a hypothesis that has a number. It's not that just that I'm assuming that it is a sphere. I am assuming that it's a sphere of certain size. Then I can check it out. Then I can check it out independently in several ways. Notice that this idea at first came as a result of some sort of a fusion of religion and measurements and building and things of that nature. Pythagoras actually had a cult. That's the Pythagorean theorem fella. Eudoxus made the first model where the Earth was in the middle. And then Aristotle made a model of Eudoxus that's complicated but very logical, and came up with the idea that the more nifty you are, the truer your version is. And as a result, for 1,000 years hence, people basically just believed Aristotle because his models were so very complicated and nifty. Aristarchus, as you've seen, came up with the heliocentric system where the sun is in the middle, but were ruled out because Archimedes' model was more nifty. And Euclid and Eratosthenes made a lot of interesting models that we don't use much more. Ptolemy made the most accurate observations and the most complicated models. Then came the people of especially Persia and southern and middle Iraq in about the 8th through the 11th century, where there was a golden age of science in the Arab Empire. And at that time, the idea of checking on the scientific method that was done in the past matured, and a person by the name of Alhazen invented optics and worked even more on scientific method. Avicenna in Persia came up with the idea that objects at rest tend to stay at rest and objects at motion are going to stay in motion in one line, and that's reversing Aristotle. And then came Occam, which was in England at about the same time, that said, no, models that are more nifty are not better. That's called the principle of parsimony, and it reverses Aristotle's idea. From there, Avicenna's model of motion begets motion went to Galileo and to Newton, that found those books because they were translated in Spain and brought to Italy and then to England, and developed what we know now as the modern classical mechanics, classical physics. Of course, it's not a coincidence that Columbus and Magellan at about the same time decided that, hey, Earth's round, we can find a way to India and we can circumnavigate the globe. Last one for you then. Try and answer this particular question just before you go home and do your homework assignment. Bum 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 go. Okay, I think you must have gotten that one. May you live long and may you prosper.